Okay, I'm going to walk through the calculus version of calculating the moment of inertia for, we can do a board pivot on the end, a board pivot on the center, and then maybe a disk. Okay, so what we already know is we know that we've memorized that the moment of inertia of a disk is 1/2 mr squared. We know that the moment of inertia of a board is 1/12 ml squared, or 1/3 ml squared, and this is pivoted in the center, and this is with the pivot on one of the ends. We actually can use the parallel axis theorem, which is really nice. All these are reviews of previous things. The parallel axis theorem says that if we want to find the moment of inertia, if you know the moment of inertia of the center of mass, then you can add an md squared term if you wanted to move the pivot. So if we assume that this is true for a board, so if we know that the moment of inertia is 1/12 for a board if we pivot in the center, and then if we want to move the pivot to an end, then we can use the parallel axis theorem to figure that out, meaning it's 1/12 in the center of mass plus md, and d would be L over 2, right? That's how far you moved the pivot squared. This is 1/12 ml squared plus 1/4 ml squared, because when you square this you get a quarter. 1/12 plus a quarter is in fact 1/3. All right, that's me using the parallel axis theorem to figure out the moment of inertia of the board pivot on the end, assuming this is true. Again, that's not what we're doing here. Now I want to show you the calculus way to prove these formulas. So let's actually do this one first. So take your board and we'll put the pivot here, and we have to go over what algebra and then what calculus means. Algebraically, we know that the total moment of inertia is the summation of all the individual masses at all their individual distances squared. So if you have a bunch of point particles, or you have a board and a point particle and a disk and they're all attached, we know that we can just sum up all the contributions. Okay, so what happens here? Well, the calculus version of that is summing up all the little BDDMs based on their positions. Well, for a board here, we're going to take this board and we're going to divide it into an infinite number of really small pieces. And then we're going to look at the contribution of all of the individual pieces. This piece has a mass, dm, and it has a thickness of dx or dr. It doesn't really matter. In this case, r is kind of our length variable, so that's got a thickness of dr. And the question is, how are those related? Okay, so let's assume that it has a uniform density, so the density of the board is uniform. So then dm is equal to what? dm is equal to m over L times dr. Think about that. That's really not that hard. That's the mass of each one of those little bitty segments is equal to the density, kilograms per meter, that's the density of our board, times the thickness of the board in meters. Kilograms per meter times meters equals the mass. For instance, if you knew that the total board had, let's say, a mass of 20 kilograms, and the board was, 10 meters long, then the density of the board was 2 kilograms per 1 meter. And so if you knew you were dividing this up into 1 meter segment, then 2 kilograms per meter times 1 meters would give you 2 kilograms, meaning 2 kilograms, 2 kilograms, 2 kilograms, 2 kilograms in each of your 10 segments. Hopefully this idea makes sense. So then we're going to replace that for dm. We're going to accumulate dm, which is m over L times dr times r squared. And we're going to accumulate all of those contributions from 0 to L. Think about what I'm doing here. This is algebraically what we know, the summation of all the point particles. Well, we have this extended object, this board, and we're going to divide it into an infinite number of point particles, each with mass dm and thickness dr. dm, we're going to make a substitution. The little bitty mass is the density of each little bitty thickness. Okay, so make that substitution in for dm, which I did, and then m and l are constants. I can factor those outside of the integral, and then I'm left integrating from 0 to L of r squared dr, which is m over L, r cubed over 3, evaluated from 0 to L. And then when you plug in L, you get L cubed over L, which is L squared, and you get 1/3 m. So we do in fact get 1/3 m L squared, and now we used calculus to figure this out. Pretty cool, right? Okay, so let's do the same thing for a board pivot on the center. Let's say we needed to prove that. Well, the nice thing is we just put it here, and we do the same integral. So we add up these contributions on this side, but all these blue contributions are the same as going this way. So we should know that the total moment of inertia in this case is just twice the contributions of the blue. So the red and the blue together are just twice the blue. The blue are me integrating from 0 to L over 2, right? To go from here, from that one, all the way to that n1 is L over 2. And then each little thing is its same dm. It's still m over L dr, each times their distance squared, r squared. And so you get this same integral, 2m over L, and you get the integral r cubed over 3 from 0 to L over 2. Okay, so think about this. This then is 2m L over 2 cubed over 3. L over 2 cubed gives you 1/8. 1/8 and 2 gives you 1/4. 1/4 and 3 gives you 1/12. M, L cubed, and L squared. Boom. See? A board pivot on the center is just 1/12 ml squared. Hopefully that sounds okay. And again, this too is the fact that the blue contribution and the red contribution is symmetrical. I've seen people do that if they put an origin here, they do something like this, and they actually integrate from negative L over 2 to L over 2 of this integral ml dr r squared. And hopefully you can understand that it's the same thing, because L over 2 and then minusing a minus L over 2 is actually going to give you just double, and it's going to give you 2 because it's some even function. Okay, so either way you're going to get this. All right, so that's the calculus way to prove this guy and this guy, and then I also showed you the parallel axis theorem to get that in case you just wanted to use that. And then we'll do one more, and we'll do the disk. Okay, we will do the disk, and the different part of the disk, even though it's very similar, is that we're going to use an area thing and we're going to use rings. So the disk is a little more complicated because we're going to go 2 dimensions. Okay, there's your disk, and we're going to pivot on the center. And again, algebraically, we need to sum up all these individual things. Well, what are the things here? Well, we need to sum up all these masses. So what shape are these masses in? For our board, they were like little bitty rectangles. Well, for the disk, they're going to be rings. They're going to be rings, and the reason is because each ring, so if I looked at this like outside ring, this part of the ring and that part of the ring and this part of the ring, see how they're all at the exact same distance? All of that ring is at the same distance from the origin. So all of that mass plays the same role because it's at the same r squared. Okay, here's the hard part. Remember, for something linear, dm was equal to m over L times dr. Okay, so now my ring isn't going to have just this, it's going to have an area. Okay, so my ring's dm is going to equal its density, which is mass over area times what? Times dA. Okay? And then what is dA? What's the area of a ring? Again, I know this is a little complicated. You got to think of that ring as a rectangle. Slice that, right? Put a slice right there, and then unravel it. This distance around is just 2 pi r. This thickness is what they would call dr. And so then dm is m over pi r squared times 2 pi r dr. And hopefully at this point in your physics career, you certainly talked about integrals, but you also talked about differentials. This literally is just the differential of a. A is pi r squared, dA is 2 pi r dr, and this is the geometric description of that. So at this point, the moment of inertia, sorry I didn't put that there, is the summation of all those. So the moment equals, we're going to sum up all the rings from 0 to r of dm, which is m over pi r squared times 2 pi r dr times r squared. I know that's a pretty complicated dm, but that's the mass of each ring. It's the density of each ring times the area of each ring. Just like over here, it was the density of each little segment times the width of the segment. This is the one-dimensional analysis, and this is a two-dimensional thing. Okay, so let's get all this out of here. First of all, those pi's can cancel, and that's a 2m and an r squared. 2m and a big R squared meaning the radius of the disk. Little r can't get factored out because it's the radius of each ring, which changes, right? It's a function. 0 to r of, what am I left with inside? R cubed dr. So 2m over r squared, and then integrating, I get r to the 4th over 4 evaluated from 0 to capital R. And this works out really nice because this is big R to the 4th over r squared, which is an r squared, and I get a 2/4, right? So 2/4 is 1/2 m, and like I said, I get r to the 4th over r squared, which is r squared, and voila, I proved to you that the moment of inertia of a disk is 1/2 mr squared, and I used calculus. Okay. I guess we have time. Let's just go ahead and do the hoop, because the hoop is actually super easy. Hoop is my favorite because it's like one step and you're done. A hoop is like this. And you're like, okay, it's the summation of all the dm's at their r squared. And you're like, oh, cool, check this out. Aren't all the dm's actually all the little bitty segments of mass? Aren't they all actually at the same r? See how they're not a function of r, and that's really just big R squared? So I can factor that out. And then, of course, the summation of all the dm is just m, and you're like, boom, done. Mr squared. You got to think about it like that, but a hoop is a collection of point particles, and all the point particles are at the same distance away. Well, if all the point particles are at the same distance away, then r is actually not a function. You see how here each ring is at a different distance away, each thing is at a different distance away? So they were a function, but they're not a function here. All of the hoop here, this hoop, I don't know, this is like the worst hoop of all time. Give it some thickness. Again, as long as it's not too thick, then they're all at the same distance away. You can factor out that little r squared is really a big R squared, so it can come outside the integral, and the accumulation of all the dm's, of course, is just the total mass. Okay, so those are the 4 things I think you should be comfortable with. Doing the board pivot in the center or on the end, doing the disk, and then of course doing the hoop. And a hoop is really just a glorified point particle with its mass just all kind of spread out. Okay.